Good day, everyone. Today we begin our fourth topic, data modeling in MongoDB. This is a crucial subject because the way you structure your data in a NoSQL database like MongoDB is fundamentally different from what you may be used to in traditional relational databases. Our main goal today is to understand the core principles of schema design in MongoDB, focusing on the trade-offs between different approaches. This will directly impact the performance, scalability, and maintainability of your applications. Here is the roadmap for our lecture. We will start by discussing the core philosophy behind data modeling in MongoDB, which is quite different from relational databases. Then we'll dive into the two primary strategies. Embedding, which is a form of denormalization, and referencing, which is a normalized approach. We will explore practical use cases for each, including advanced patterns like the bucket and subset patterns. Finally, we will consolidate this knowledge by establishing clear decision criteria to help you choose the right model for your specific needs, and we'll touch upon the practical aspects of indexing and managing schema changes over time. Let's begin with the core philosophy, which represents a significant paradigm shift from the relational world. In SQL, we are rigorously trained to normalize data, to eliminate redundancy at all costs by splitting data into multiple tables. MongoDB's philosophy is fundamentally different. The primary goal is not theoretical data purity, but practical application performance. The guiding principle is simple yet powerful. The way you structure your data should be a direct reflection of how your application will query and use that data. Instead of starting with the data, we start with the application's use cases. What information does a user profile page need? What data is required to render an order summary? The answers to these questions shape our schema. This approach, often called schema on read, prioritizes read efficiency. We are willing to accept some data duplication if it means we can retrieve all necessary information for a specific view in a single, fast database operation. This minimizes latency by avoiding complex server-side joins. Therefore, the entire process of data modeling in MongoDB boils down to one critical, recurring question for every relationship between entities. Do we embed the related data within a parent document for fast access, or do we store it separately and link to it using references for greater flexibility? We will spend the rest of the lecture exploring the implications of this choice. Our first major strategy is called embedding. At its core, embedding is a form of denormalization. Instead of splitting related data into separate tables, we intentionally group it together by storing child data directly inside a parent document. This can be done in two ways, either as a single nested object, which we call a subdocument, or more commonly as an array of subdocuments. It's crucial to understand that this approach is not a universal solution. It is specifically designed for what we call one-to-few relationships, where a parent entity is related to a small, manageable number of child entities. Think of a blog post and its comments or a product and a handful of reviews. The ultimate goal here is pure performance. By placing all related information in a single document, we enable the application to retrieve everything it needs to render a complete view, like a product page with all its reviews, with a single atomic read operation from the database. This eliminates the need for costly joins and dramatically reduces query latency, which is a key advantage in modern, high-performance applications. Let's make this tangible with a classic e-commerce example. A product and its user reviews. In this scenario, the reviews don't really have an independent identity. They belong to the product. When a user navigates to a product page, the application needs to show the product's details and its reviews simultaneously. This is a perfect one-to-few relationship. We expect a product to have dozens, maybe hundreds of reviews, but not millions. Because the child data, reviews, is almost always needed with the parent data, product, and the relationship is bounded, embedding becomes the most logical and high-performance modeling choice. Here you can see the actual JSON representation of our product document. Notice that it's a single self-contained unit. We have our top-level fields like ID, name, and price. The most important part is the reviews field. It's an array denoted by the square brackets, and each element within it is a complete JSON object, a subdocument, with its own fields like username, rating, and so on. The beauty of this model is its efficiency. To render the entire product page, Our application executes just one simple find query using the product's ID. A single database operation returns all this data. This is incredibly fast. Furthermore, this design provides atomicity. If you need to add a review and, in the same operation, update the product stock level, you can do so in a single atomic write operation on this one document, which guarantees data integrity. Now that we've seen how embedding works, let's summarize its powerful advantages. The most significant benefit, and the primary reason we choose this model, is performance. By collocating data, we allow the application to get everything it needs for a specific view, like a product page, in one single trip to the database. This is fundamentally faster than a relational approach requiring joins. This leads directly to the second point. We drastically reduce query latency by avoiding those complex server-side operations. A simple find is much less resource-intensive than a multi-stage aggregation with a lookup. Finally, a crucial advantage is atomicity. MongoDB guarantees that any write operation on a single document is atomic. This is incredibly powerful. It means you can, for example, add a new review to the array and simultaneously decrement a product stock count in the same operation. You are guaranteed that either both of these changes happen, or neither of them does. This simplifies your application logic and ensures data integrity without the overhead of complex transactions. However, embedding is not a universal solution, and it comes with significant trade-offs. The most important one to remember is the strict 16 megabyte size limit for any single document. While 16 megabytes is a lot of text data, it is a hard limit that you cannot exceed. This limit makes embedding completely unsuitable for relationships with unbounded growth. Think of a logging system where a host generates millions of log entries, or a popular product that could accumulate tens of thousands of reviews. If the array of subdocuments can grow indefinitely, you will inevitably hit the size limit, and your application will start seeing write failures. This is a critical design constraint. Another issue is potential read inefficiency. Imagine a catalog page that only needs to display a list of product names and prices. With our embedded model, the query would still retrieve the full document for each product, including the potentially large and, in this context, completely unnecessary reviews array. This is called overfetching, and it wastes memory and network bandwidth. Finally, if you embed information that can change and is shared, like detailed manufacturer data, you introduce data duplication. If the manufacturer updates their information, you now have to perform a complex and slow operation to find and update every product document where this data was embedded. Now let's look at a very clever application of the embedding model called the bucket pattern. This is a crucial technique for anyone working with high-frequency time series data. Think about data from IoT sensors, application logs, or real-time analytics, where you might be receiving thousands of data points every minute. The naive approach would be to create a new document for every single measurement or event. This is a major anti-pattern in MongoDB. It leads to two significant problems. First, the storage overhead is huge, as every small document has its own ID and field names. More importantly, the index becomes enormous. A massive index consumes a lot of RAM and severely slows down write operations, as it needs to be updated with every single insertion. The bucket pattern solves this elegantly. Instead of one document per event, we create one document per time period. We group or bucket all the events for a given hour or a given day into a single document. Instead of creating a new document, the application just appends the new data point into the correct bucket document for the current time period. Let's analyze this example document from a sensor readings collection. Instead of 60 separate documents for each minute's reading, we have just one. Notice the key fields. We have a sensor ID to identify the source, and a clear time window defined by start date and end date. The actual data points are appended to the measurements array. Each element is a small subdocument with a precise timestamp and the measured value. But here's a very powerful feature of this pattern. We can pre-aggregate data directly within the bucket. See the transaction count and sum temp fields. By calculating these sums as data comes in, we make future analytical queries like finding the average temperature for the hour incredibly fast. The database doesn't need to scan all 60 individual measurements. It can just use the pre-calculated sum. This design dramatically reduces the total document count and the size of the index, which leads to exceptional performance for time-range queries. We now turn our attention to the second major data modeling strategy, referencing. If embedding is about denormalization, referencing is the opposite. It aligns with the principles of a normalized data model, which should be very familiar to anyone with a background in SQL. The concept is straightforward. Instead of nesting the actual data, you store a link to it. This link is simply the unique ID of the related document, which resides in a separate collection. This is conceptually identical to using foreign keys to link tables in a relational database. This model is the preferred, and often the only viable choice when dealing with relationships that are not one-to-few. We use it for one-to-many relationships, especially when the many side is very large or can grow without bounds. It is also the standard way to handle complex many-to-many relationships, which we will discuss shortly. Essentially, if you can't embed it, you should reference it. To see referencing in action, let's consider a very clear one-to-many relationship: publishers and the books they produce. A large publisher might have a catalog of thousands of books. If we tried to use the embedding model here, we would place an array of book subdocuments inside the publisher document. This array would grow with every new book published and would inevitably crash into the 16 megabyte document size limit. It's an unbounded relationship, so embedding is simply not an option. The correct approach is normalization. We create two distinct, separate collections, one for publishers and another for books. Then, within each book document, we will store a single field that contains the ID of its publisher. This creates a lightweight, scalable link between the two entities. To retrieve a book along with its publisher's details, our application will need to perform two separate queries or use a specific aggregation stage called lookup, which mimics a join. Here we can see the practical implementation. First, we have our publisher's collection, where each document represents a single publisher with its own unique ID. Second, we have the books collection. Look closely at the documents here. Each book has its own data, like title and page count, but critically, it also has a publisher ID field. The value of this field is the object ID that matches the ID of the publisher in the other collection. This simple reference is the link. It's lightweight and incredibly scalable. We can now add millions of books to the books collection, and it will have no impact on the size of the publisher documents. This model perfectly handles the one-to-many relationship at scale. So, what are the primary benefits of this normalized approach? The most significant advantage is improved data integrity and management. By avoiding data duplication, we establish a single source of truth. Information about an entity like a publisher exists in exactly one place. This makes updates incredibly simple and reliable. If a publisher changes their name or location, we only need to modify a single field in a single document. This change is instantly and consistently reflected for all related books, eliminating the risk of data anomalies that can arise from duplicated information. Furthermore, this model places no limits on the scale of a relationship. A publisher can be associated with 10 books or 10 million. Because each book is its own small, separate document, we will never run into the 16 megabyte size limit, no matter how large the relationship grows. Finally, this separation allows for more efficient and granular access patterns. If our application needs to display a list of all publisher names, it can run a very fast query on the compact publishers collection without being forced to load any of the potentially huge and irrelevant book data. This completely avoids the overfetching problem. Of course, this model also has trade-offs. The most significant one is the impact on read performance. Because our data is now split across different collections, we can no longer get everything we need in a single simple database read. To reconstruct a complete object, for instance, a book with its full publisher details, the application has to do more work. It must either issue a second query to the publisher's collection or use the aggregation framework's lookup stage. While lookup is a powerful tool that mimics a join, it is inherently slower and more resource-intensive than reading a single self-contained document. The other critical point, especially for those coming from a SQL background, is that MongoDB does not enforce referential integrity. It is entirely possible to delete a publisher document while books still reference its ID. This creates what we call orphan references, links that point to nowhere. This means the responsibility for maintaining data consistency shifts from the database to your application. Your code must be carefully designed to manage these relationships, for example, by performing two-step updates or cleanups when a document is deleted. This adds a layer of complexity to your application logic. While one-to-many relationships are common, many applications need to model more complex many-to-many associations. A classic example is students in academic courses. One student can enroll in many courses, and one course can have many students enrolled. The standard and most effective way to implement this in MongoDB is with a technique called two-way referencing. It is a very powerful application of the referencing model. The mechanism is quite logical. The student document will contain an array of all the course IDs they are enrolled in. Symmetrically, the course document will contain an array of all the student IDs enrolled in it. This design provides maximum flexibility and is highly optimized for read operations. If you want to find all courses for a given student, you query the student's document. If you want to find all students in a given course, you query the course's document. In both cases, the query is simple and fast. The main trade-off, as we'll see, is that write operations become more complex. Let's examine the structure. In the students collection, each document, in addition to student information, contains a course IDs field. This is an array that stores the ID of every course the student is enrolled in. Symmetrically, in the courses collection, each document contains a student IDs array, which stores the ID of every student attending that course. This two-way referencing model is extremely efficient for reads. Want to find all courses for Alina? It's a single query to the students collection. Want to see all students in the database technologies course? A single query to the courses collection. It's very fast. However, as I mentioned, the trade-off lies in the complexity of write operations. When a student enrolls in a course, our application must perform two updates. Add the course ID to the student's array, and then add the student's ID to the course's array. This requires more sophisticated application logic. We've now covered both models in detail. So how do you choose? The selection is not about a single correct answer, but about making a calculated trade-off. The foundational principle to always keep in mind is, data that is accessed together should be stored together. Your decision should be guided by a careful analysis of three key factors. First, the cardinality of the relationship. Is it one-to-one, one-to-few, or one-to-many? Second, your application's data access patterns. Will you almost always need the related data, or will it be queried separately? And third, your requirements for atomicity. Do you need to update related entities in a single, indivisible operation? This table provides a concise summary of our decision-making framework. Let's quickly go over it. For relationships, if you have a one-to-few scenario, lean towards embedding. For anything larger, one-to-many or many-to-many, referencing is the correct path. For data access, if the parent and child data are almost always queried together, embed them to maximize read performance. If they are often accessed separately, use references to avoid fetching unnecessary data. For atomicity, if you require that updates to the parent and its related items happen as a single, all-or-nothing transaction, embedding is your only option, as it relies on single document atomicity. Finally, for data size, if the set of related data is small and its growth is bounded, embedding is safe. If the data set is large or can grow indefinitely, you must use referencing to avoid hitting the 16 megabytes document size limit. Now let's look at a very clever hybrid solution called the subset pattern. This pattern directly addresses one of the major disadvantages of embedding, the problem of large documents and overfetching. Imagine our product document again. A popular product might accumulate thousands of reviews over time. However, the main product page probably only displays the 5 most recent or most helpful reviews. Loading the entire document with all 2,000 reviews just to show 5 is incredibly inefficient. The subset pattern solves this elegantly. In the main product document, we embed only a small, curated subset of the data, for example, an array called recent_reviews that is always trimmed to the last 5 entries. Then we store the complete, unabridged list of all reviews in a separate reviews collection, using a reference back to the product. This gives us the best of both worlds. The most common read operation, loading the product page, is extremely fast because it reads a small document. The less frequent operation of a user clicking "See all reviews" is handled by a separate, dedicated query to the full reviews collection. Here is the implementation of the subset pattern. Look first at the products collection. The document is small and efficient. It contains a field like review_count for summary information, and most importantly, the recent_reviews array, which is always kept small, maybe 2, 5, or 10 entries. This is the document we fetch for the main product page. Separately, we have a reviews collection. This collection holds the complete, unabridged data. Every single review is stored here as its own document, with the product ID field that references back to the parent product. The application logic for writes is now more complex. When a new review is submitted, the application must perform two operations. First, it inserts the new review into the main reviews collection. Second, it updates the recent reviews array in the products document, pushing the new review in and removing the oldest one to maintain the subset size. This complexity on the right path is the price we pay for highly optimized read performance for our most common use case. The choice between embedding and referencing has a direct and profound consequence on your database's indexing strategy and, therefore, its query performance. It's critical to understand this link. When you use the embedding model with arrays, MongoDB employs a powerful feature called multi-key indexes. If you create an index on a field within an array, like the username inside our reviews array, MongoDB doesn't just index the array as a whole. It creates a separate index entry for every single value in that array. This is extremely powerful, as it allows for highly efficient queries to find, for example, all products reviewed by a specific user. In contrast, the referencing model relies on standard single-key indexes, just like in a relational database. You would typically create an index on the reference field itself, for instance, on the publisher ID field in the books collection. This index makes it very fast to look up all documents that relate to a particular parent, like finding all books for a given publisher. Understanding this distinction is absolutely critical for performance tuning. Finally, let's address a very practical challenge. In any real-world project, your application's requirements will evolve. This means your data model will also have to change. The flexibility of MongoDB's schema is an advantage here, but it can lead to a situation where you have documents with different structures coexisting in the same collection. The schema versioning pattern provides a systematic way to manage this. The core idea is simple. You add a versioning field, like schema_version, to every document. When you introduce a breaking change to the schema, all new or updated documents are written with the new version number. There are two main strategies for handling old documents. First, your application code can do it on the fly, transforming data in memory. Second, you can run a background migration script that finds and updates all old documents in the database. This pattern is essential for maintaining stability in a production environment. Here is a simple example of what a version document looks like. We have our standard user data, but notice the last field, schema version, which is set to 2. Let's imagine that in version 1, the name was just a single string, name, John Doe. After deciding to change the model to a more structured object with first and last names, all new documents like this one are created with schema version 2. The application can now reliably identify the structure of any user document it reads by simply checking the value of this field. It's a simple but very robust pattern for managing schema evolution over the lifecycle of an application. To help consolidate what we've learned, here are 3 questions for you to consider. They touch upon the core philosophy, the practical limitations of embedding, and the standard approach for complex relationships. Take a moment to think about how you would answer them. If you're unsure about any of these, I encourage you to review the relevant sections of the lecture. Answering these will be a good indicator of your understanding of today's key concepts. The complete list of 10 questions is, of course, in your lecture notes for a more thorough review. That brings us to the end of our lecture on data modeling in MongoDB. We've covered the core philosophy, the 2 main strategies of embedding and referencing, and several advanced patterns to handle real-world challenges. I hope this gives you a solid framework for designing efficient and scalable schemas for your own applications. If you have any further questions as you review the material, please feel free to reach out via email. Thank you.